Good morning, everyone. I would like to discuss distributed mutual exclusion and elections from distributed systems today. So, what all about distributed mutual exclusion? So, we use this concept for concurrency control, where multiple processes are willing to enter into the critical section. So, what is critical section? It is an area where actual execution process starts and ends. So, any process willing to enter into the critical section, if a number of processes at a time simultaneously want to go into critical section, then we'll get a problem called concurrency. So to overcome this problem, we use distributed mutual exclusion concept. So here in this, it is an application level protocol for executing a critical section. So what are the essential requirements for distributed mutual exclusion means? Here we have three properties which need to be satisfied for any distributed mutual exclusion algorithms. So here we have three properties. That first property, mutual exclusion one, which is a safety property. The second property is liveness property, and the third property is ordering property. So what is safety property means? It, like every process, at least one process should always there in a critical section, which means it should not be empty. The critical section area should not be empty. And what is the second property? Liveness property means here the request to enter and exit the critical section should be eventually accepted, which means every time we should not we should not accept it, and we should always accept every process who want to enter into the critical section, which should be eventually succeed. And the third property is one request to enter critical section happened before another, then try entry to the critical section is granted in that order. It should be followed the happened before relationship, so that the relation of the process which has happened before the next process should be entered into the critical section. That is a real rule we need to follow. So if these three rules, safety, liveness, and ordering are followed, then we can say that the particular algorithm is exhibiting distributed mutual exclusion concept. So we have three main sections we have here, like entry section, resource access section, and the exit section. So entry section is a section where to enter into the resource access section, that is nothing but critical section. We need a code to enter into that. So that code will be available in the entry section. And in the resource access section, which is nothing but a critical section where the actual resources will be shared among the processes. And the exit section is a section where it will leave the critical section, and so that the other processes may easily enter into that critical section. So these are the three sections which are there in the distributed mutual exclusion. And we need to talk about the performance evaluation of distributed mutual exclusion, which is nothing but here we have some message complexity, which is nothing but how many messages are required to enter into the critical section. That is nothing but the value, the number of messages. We can take it as a value. That value will be considered as a message complexity of a distributed mutual exclusion. And also we need to calculate the synchronization delay. The synchronization delay is nothing but whenever the old site or the old process, the process which is already available in the critical section wants to leave that particular critical section, and the time gap between the old site and the new site which want to enter the critical section, the old site which is willing to leave the critical section, the time gap between two sites will be cause a delay, which we call it as synchronization delay. And we have one more performance evaluation technique or metric, which we call it as response time. The response time will be calculated using a formula. Whenever a particular site or a process want to enter into the critical section, it will be sending a request. So this request will be sent out, and this whenever the critical section is idle, I mean when there is no other process is willing to go, then the request will be accepted. The request will be accepted, and the particular process will be entered into the critical section. And after that, after entering into the critical section, after its process completed, it will be leaving back to the critical section. So that time, whenever a process requests and it leaves the particular site, that complete time is noted as response time. And the last point we need to discuss is throughput, system throughput, which is we can be calculated using a formula 1 by SD plus E, where SD is nothing but synchronization delay and E is the average execution time. So these are all the performance evaluation metrics of distributed mutual exclusion. Under distributed mutual exclusion, we have like several algorithms like central server algorithm, and ring-based algorithm, and using multicast and logical clocks. And there's nothing but Ricard Agarwal algorithm. And also we have Mekabus voting algorithm. So these all algorithms comes under the examples of distributed mutual exclusion. So now we'll discuss central server algorithm, which is you can see this diagram, right, where we have a server, and under the server we have like 4 processes, where process P1 is sitting in idle, and process P2 is requesting for a token, and process P3 is releasing token, which because it is already entered into the critical section and it has used its a particular time for a particular period of time, and it want to release that token so that the other process can use it, right? So P3 is releasing the token, and P4 will be, and server granted a token to the P4 here, because why it is not granted to P2 means P2 and P4 are waiting and want to enter into the critical section, but P4 has sent the request first. So server will be following first come first serve rule. So based on who came first, for those processes, we'll be giving the token the first. So that is a thing will be happening in the backend of central server algorithm. And coming to the ring-based algorithm, it is completely completely based on a process. It doesn't have any master process. Here the processes will be sending the tokens one by one, which will be sent in one direction, that is clockwise direction. Whenever a process doesn't need a token, it will be simply forward that particular token into the next neighbor. So here, this will be like a clockwise sending of tokens from one person to other person, from one process to other process. That is a process in a ring-based algorithm. And coming to using multi-classed and logical clocks, what is the concept in this means? Here we use clocks instead of depending on the server, or instead of depending on some other process to be sent, whether a token will waiting for a token, we use here a clock. A clock is a concept where we use a timestamp of a particular process who sent the first. The process who sent the request first will get a chance to enter into the critical section. That is a process used in using multi-classed and logical clocks. So how will we identify the particular process who sent first the request means based on the clock timestamp. Based on the timestamp, we will be identifying which process has sent the request first, and the process who sent the request first will be given a permission to enter into the critical section. This is all about the multicast and logical clocks. And the last algorithm which we need to discuss in the distributed mutual exclusion is Mekabus voting algorithm, and this algorithm is all about based on voting. So the process which want to enter into the critical section will be asked all other processes that particular process want to enter into the critical section. So if every process voted as yes, then the particular process will be entered into the critical section without any delays. So here in this algorithm, the importance of this algorithm is that here there is no need of waiting for large times. So here the process, whenever it want to enter the critical section, directly it can ask for the other process to vote for voting, and when it gets a reply as yes from all the processes, it directly enters into the critical section. That is all about the Mekabus voting algorithm. And coming to the next concept in our session, we will discuss about elections. Here, elections. Coming to elections, we know we are in a daily average basis. We can understand what is an election. Elections are generally a term used for electing some person who want to enter into some process. So here, this election concept is for especially for electing a coordinator. So to elect a coordinator, we use a concept called election. So how we will be electing a coordinator? What is the process behind that? So here, to elect a coordinator, we use some concepts like we will give preference to the highest process number. I mean process identifier number. The process who is having largest process identifier will be given a first priority. And for that, we have types of some examples we have under this elections concept. So first we will discuss a ring-based election algorithm. It is completely a ring type of concept where we will have processes will be arranged in a ring based, and every process will have its own process identifier. And here, this will be like initiated whenever a particular process has crashed. The other process who identified the particular process has crashed So the particular process, the particular process should be a coordinator first. So if any coordinator who has crashed and not giving any reply back, so the particular process who identified that will be initiating the process and will be sending a message, election message, by including its own identifier value in the particular array. So he will be sending all these process identifier values in the array format to the next neighbor process, and this process will be continued till again the process who initiated this process will be the last person getting this message. So by seeing these messages, by seeing these election messages, by noting down all the process identifiers, the process who initiated the election message, the elections who initiated will come to know that the process who is having the largest process identifier will be elected as a coordinator. This is the concept in a ring-based algorithm. And coming to the Bewley algorithm, which is an example of election algorithm. And in this algorithm, the process is like, here, let us consider with an example where we have process P1, P2, P3, and P4. Here, process P4 is already a coordinator, but he has crashed. So when P1 has sent a message to the P4, that P1 came to know that the P4 is no more working, no more in a working condition. So P1 will send an election message to P2 and P3, and P2 and P3 will send a reply back to the P1. So whenever P1 gets a reply back from the P2 and P3, P1 will come to know that P2 and P3 is having the highest process identifier than P1. So P1 will stay silent in the stage 2, and P2 and P3 will be sending again selection messages to the P3 and P4. And in the stage 3, we can the P2 will come to know that P3 and P4 are again crashed. So P2 itself will identify himself as he is the coordinator of the next coming process. So P2 will send a coordinator message to all the processes that he is the coordination, that the particular process is the coordinator for the next coming session. So this is all about the election algorithms. So yes, so this is all about distributed mutual exclusion and elections using some algorithms. Yes, thank you.